Installation of flow meters part 2. Installation of flow meter components. Lecture series on installation of flow meters. This lecture series consists of following lectures. Installation of flow meters part 1. This discussion considers primarily the installation of modern differential pressure transmitter, that is DP cell. Second lecture is installation of flow meters part 2. In this lecture we talk about the components for installation of flow meters. Third lecture is installation of flow meters part 3. In this lecture we talk about the flow element or the primary instrument installation. Process, containment and safety. Piping specifications and code requirements must be respected and applied from the process piping to the instrument side of the process block wall. Because the impulse lines are small diameter and are not exposed to the same temperature as the flowing stream, it is common to use user-defined standards and specifications for these requirements. Components. Impulse lines. The impulse lines or lead lines are the interconnecting piping lines between the process and the transmitter and are an integral component of the measurement system. Errors exist if there is any difference in pressure in one impulse line between the primary and the secondary, unless exactly the same difference exists in the other impulse line. Many head type, orifice, flow nozzle, venturi etc. flow meter installations have installed accuracy seriously compromised by poorly designed or installed sensing lines. In this lecture, we will discuss these problems and make recommendations. Request. It is hoped that this session is going to be useful to you. Please press like. Please subscribe. Impulse lines for gas service. In gas service, it is necessary to have a completely open pathway for the gas in the impulse line. Any pocket with trapped liquid will lead to significant error. In gas flow, the impulse line absolutely must be perfectly leveled or sloped up to the secondary. It is common to have flowing gases with drops of liquid or vapors that can condense in the impulse line. It is necessary that any drops of liquids flow down and back to the process connection. If there is any dip in the line where liquids can collect, then there will not be a continuous open gas passage. In gas service gases, it is possible to have other gases with a different density to accumulate. If the transmitter is far above the secondary, there may be an apparent difference in the content of the two impulse lines and some error introducing an error. Impulse lines for liquid flow services. In liquid flows, the impulse line must be perfectly leveled or sloped up towards the primary element to allow any non-condensable vapors to rise and leave the line. The traditional minimum slope specification in either case is 1 vertical to 12 horizontal. Impulse lines for liquid flow services. The problem is that the farther apart the flow element and the DP device are separated, the less certain we are of the fluid situation in the line. With liquids, the level effect is far more severe because of the greater liquid density. In the process industries, liquid streams are notorious for having strange liquids appearing during upset conditions or during maintenance. For 24/7 processes which may run continuously for years, it is certain that anything that can happen will happen, and these will not be noted in the operating logs. Dirt or corrosion particles will be everywhere. A very small difference in composition can deliver enough of an impurity throughout the process in quantities to accumulate where they are least desired. Impulse line size. It is also necessary that the impulse lines have adequate diameter to permit free flow, considering imperfect alignment, deflection, and sagging in horizontal runs, surface tension, and the capillary effects. Common standards specify a minimum of 15 mm, that is half-inch pipe, with 40 mm, that is 1.5 inch, in condensing vapor service. Some standards advise larger sizes for greater separation to improve drain and vent properties. Some standards and references have tables of larger diameter for longer impulse lines. These must be considered carefully. Freeze Protection. If the fluids involved can be exposed to the temperatures below their freezing point, or for vapors exposed to condensing temperature, it becomes necessary to heat the impulse lines. Low pressure steam or electric heat trace cable is a typical choice. For extreme conditions, jacketed pipe or tubing has been used. Cost will affect the choice. Some users have filled exposed liquid filled lines with an antifreeze mixture to protect them. If this is done, it will be necessary to replace this mixture on a scheduled basis to maintain a known mixture despite diffusion of liquids in or out of the impulse lines and consequent drift in apparent instrument calibration. Resonance in impulse lines. Metering errors have been attributed to acoustic resonance in the impulse lines in gas flows. The simple cure is to minimize line length. Any attempt to hide the noise by restricting flow in the impulse lines with a valve or by pinching the line might make the gauges and recorder look nicer. However, this will cause an unpredictable error because the flow is proportional to the square of the pressure difference. Filtering of noisy pressures smears the data, and the average difference will not be accurately proportional to flow. The price of making the recorder or data display look pretty is lost information. Prediction of any acoustic resonance frequency is difficult, and it will change with any change in temperature or pressure in the line. Impulse lines will have connections and routing unknown during the design phase. The transmitter itself will have time constants. In general, there is little that can be done. For very special measurements such as at flow laboratories and special short tests, it may be necessary to revise impulse line arrangement and length to detect and then resolve problems. Some flow tests for valves and flow meters use very short flow times due to flow limitations in the laboratory facility. Where a reciprocating pump or similar source of pressure or flow fluctuations causes a very noisy signal, the ideal solution is to find another location where the pulsations are small enough, less than perhaps 10% of the measured pressure difference. Some users have added a surge suppressor in the flowing fluid, such as a tank with compressible gas volume, that is air-filled flexible bag, to smooth out the pressure variations. Process connections. The process piping specifications define the requirements from the piping or process connection to the outlet of the first block or isolation valve. The flow meter standards set the diameter for the pressure tap for the given pipe size and specify that the inside end of the bore is smooth with no imperfections or burrs. For important flow meter installations, it is important to inspect and measure the orifice bore, measure the actual pipe internal diameter, and inspect the condition of the pipe for excessive roughness. It is important that the process block valve be either a ball valve, or if a gate or globe valve is used, it be installed with the valve stem horizontal to avoid introducing a pocket in the line. Manifold. The assembly of connections and valves between the impulse lines and the secondary to allow convenient calibration and replacement of the sensor. Fabricated manifold. The manifold is the set of valves found at the transmitter that are installed to permit replacement or calibration in place. A 3-valve manifold allows isolating the transmitter from the process pressure and then opening the bypass or equalizing valve to permit adjusting the transmitter for zero signal output at the operating pressure and ambient temperature. 5 valves can provide a double block and bleed arrangement or a more convenient way to vent or calibrate the transmitter. Figure in next slide shows a fabricated manifold. Assembled manifold block valves. This diagram shows manufactured manifold. Manufactured manifold. A manufactured manifold replaces individual valves and fittings. This is a typical block of metal with input and output fittings and the valves all in one package. These are manufactured in many variations. Some have vent plugs and calibration fittings. The result is cost savings and reduced probability of leaks. Figure is shown. The connections are spaced to suit the transmitter and orifice flanges. These are often purchased component with instrument mounting brackets. Compare these with the assembled manifold in the figure in next slide. Assembled manifold block valves. Remote diaphragm seals. In some difficult situations, such as very high temperatures, high viscosity, nasty chemicals, or for some primary elements, a chemical seal is used. The wedge flow element is an example. They are also used in some tank level measurements. Because the isolation diaphragm is not perfectly flexible, there is some reduction in sensitivity. Larger diameter chemical seals are thought to be more sensitive but more subject to damage. The tubing, typically small diameter liquid filled capillary tubing connecting two seals to the transmitter, should be of the same length to reduce the effects of ambient temperature and thermally insulated together where possible. Follow the manufacturer's instructions carefully. Some of these cannot survive pressures or vacuums much beyond normal operation. Even allowing one or the other seal to be too far below the transmitter can cause failure of the diaphragm if that elevation creates an excessive internal pressure due to the density of the fill fluid and the difference in created pressure is higher or lower than it can withstand. For seal applications in closed systems, normally at positive pressures, it is possible to create substantial subatmospheric pressures when the system is shut down and cools. This may lead to failure. The prudent engineer will specify the working conditions for any sealed system. The maximum pressure to specify is the failure pressure of the vessel or piping or the relief valve set point. For minimum pressure, use full vacuum unless the system has some vacuum protection. It is risky to use the flow sheet values for maximum and minimum pressures and temperatures. Recent developments. Some schemes and products such as the compact flow meter to reduce costs and improve reliability have been already mentioned. It has been suggested that it would be better if the DP transmitter is mounted with the pressure tabs facing up in liquid service to permit any gases trapped in the input diaphragm chamber to escape up and get out. For similar reasons, the transmitter tabs would face down in gas service. Definitions. Primary element in flow service. Typically an orifice plate, insert flow tube, venturi tube, cone meter, pitot tube, averaging pitot tube, which has a predictable relationship between flow and pressure difference. Secondary element or secondary. The indicating gauge, manometer or transmitter displaying or transmitting a signal derived from the sensed pressure or pressure difference. Impulse line. The tubing or pipe conveying the sensed pressure from the process connection primary element to a transmitter or indicator secondary element. Request. It is hoped that this session was useful to you. Please press like. Please subscribe.